Good afternoon, everybody. Please take a seat. Thank you very much for coming. It's a great pleasure to have with us Professor John Bahcall from the Institute of Advanced Study in Princeton. He got the Vanderbilt Prize. And John is not only a great scientist, but he's also a great friend of Israel and a great friend of Tel Aviv University. And when I look around, I can see one person who can perhaps introduce him better than anybody else. And it's my pleasure to call Professor Yuval Neiman to introduce the speaker.
I'll start in Hebrew because, the topic is John and Israel, so it's probably better to start in Hebrew. אני רואה במפגש היום, מבחינתי, סגירת מעגל שלמעשה נפתח לפני 40 שנה. זה רק אומר שאנחנו שייכים לדור שהוא לא כל כך רענן, אבל אני פה רזים, אבל אני אספר על כל פנים איך הגיע ג'ון לישראל ולמעשה את ההתחלות שהיום אנחנו כותבים את הפירות שלהם. ג'ון למעשה פגשתי אותו בקלטק ב-1963 כשהגעתי לקלטק, והוא היה אחרי מעבר, כמו שמענו אתמול, מ3 שעות לימודי ספורט ביום או משהו, עבר כבר לפיזיקה ולאסטרופיזיקה, ואני פעלתי מזה שבקלטק הפיזיקאים הגרעיניים עסקו באסטרופיזיקה בחלקם הגדול, והמלצתי על כמה מהאנשים שמשל פרופסורים פה בתל אביב לעשות דבר דומה, ואופן כיוונו אותם לכיוונים של לימודי אסטרופיזיקה, ניצול של העניין. וג'ון עסק באותם הימים, היה בקבוצה של וילי פאולר והגרעינאים האחרים שבעצם בהמלצת פרד הויל נכנסו לבעיית הנוקליאוסינתזה, האבולוציה של החומר ביקום. החומר שעכשיו אנחנו יודעים שבסך הכל רק 5% מהחומר שישנו ביקום. לפני שיצאתי לאמריקה, שכנעו אותי גם להצטרף לוועדה של המייעצת של בת שבע ברוטשילד, שישב ברחוב על יד הקמפוס הזה לפני הקמפוס, בכל הקמפוס. ובת שבע ברוטשילד נמנע אז פעילויות מדעיות שונות, ואני הצעתי שבפעם ראשונה בישראל נעסוק בנושא של חלל ושל אסטרונומיה, וקבענו נושא כזה לשנת 1964, ולכן כשהגעתי לקלטק חיפשתי מתנדבים כאלה שאפשר ללמוד מהם משהו בארץ, כשבארץ עוד לא עסקו בנושא הזה של אסטרונומיה. ובמגעים עם ג'ון ובידידות שנוצרה במקום, הסתבר לי שהוא בהחלט בשל לבוא לארץ וליצור פה קשרים וללמד קצת. וגם לפעמים יש רוח נבואה, ואני אמרתי לו שזה גם המקום שבו הוא ימצא ודאי נערה ישראלית חביבה, וזה יהיה לטובה וזה יתגשם. אגב, חשבתי שעד לפני שבועיים חשבתי שזה ההישג היחידי שלי בכיוון הזה, ועד שנתתי סמינר לפני שבועיים בבאר שבע, וניגשו אליי פרופסור ואשתו, ואמרו, אתה יודע שאתה שיתפת בינינו. אם עוד יימצא שלישי, אני אהיה מאוד משוכנע שזה משהו בכישרון קבע. עכשיו, לחזור לעניין, ג'ון למעשה היה בתחילה, תמיד עסק באסטרופיזיקה במשמעויות הרחבות ביותר. יחד עם זה, הייתה בעיה אחת שהוא עלה עליה מאוד מוקדם, זה רעיון האסטרונומיה של הנייטרינו, להשתמש באותו חלקיק חמצמק שמסוגל לצאת מן השמש ולהגיע לכאן ולהגיד מה שקורה שם במרכזה, והוא שיתף פעולה עם דייוויס ואחרים אחרים שעסקו בזה, ודי מהר גילה אפקט שיכולו להיות לו שני פירושים, או פירוש אסטרונומי או פירוש פיזיקלי, או פיזיקה אחרת, האפקט הזה של היעלמם של הנוטרינו בדרך מהשמש הנה, או שהם לא נוצרו, או שמשהו בשמש שונה, או שהפיזיקה שאנחנו לומדים צריכה זקוקה לתיקון לגבי מה שיכול לקרות לנוטרינו בדרך. והוא התעקש ועמד מאחורי קיום הפרדוקס, קיום הבעיה, גם כאשר רבים מאוד לא קיבלו את זה ואמרו את זה פלוקטואציה סטטיסטית. היו כמה שנים ששמעתי פה בארץ גם כן כמה מידידינו שלא האמינו בעניין, ואמרו זה מקרה, זה משהו פלוקטואטיבי וכו'. ובסופו של דבר, במדידות שהראו בשנים האחרונות, גם בקנדה, גם ביפן, הסתבר שבדיוק, א', שהמודלים של השמש דווקא היו בסדר, ושהתוצאה היא בפיזיקה. בפיזיקה שבין השמש לבינינו, פשוט השפעה של הזמן ושל החומר. לפני שהנוטרינו יוצא, הוא צריך לעבור דרך הרבה חומר בריוני, והוא עושה אינטראקציה כלשהי איתו, שגם עליה למדנו משהו, בעזרת הידיעה שיש אפקט. אז ג'ון תרם תרומות חשובות לאסטרופיזיקה פרט לזה. יש ועדות של האקדמיה האמריקאית שהוא עמד בראשן וקבע פרוגרמה לשנים רבות. הוא ידו בהרבה דברים ועשה רבות בעניין זה. אני רק רוצה לומר עוד סיפור קטן. שמענו בעצם מנטע עכשיו הרצאה על מה שנקרא היום אנרגיה האפלה. אני במאמר בכתב העת המדעי החשוב הזה, ראש גדול, שזה כתב עת לילדים, חשבתי איזו בעיה תישאר עדיין בעיה כאשר הם יגדלו ויצטרכו לפתור את הבעיה. אז נדמה לי שהבעיה הזאת היא בעיה שנפתחה היום, וקראתי לה הפן הדוחה של כוח המשיכה. זה מה שהסתבר שיש לו פן דוחה, ואנחנו רק לא מבינים עוד איך הוא פועל הפן הזה. אז כל מי שרוצה לקרוא עוד על מה שעשה ג'ון בהקשר הישראלי, יקרא בחוברת שלי שיצא מטעם האקדמיה על 70 שנות פיזיקה בישראל. אני אומר שמה שחלקו רב בגידול הפיזיקה הישראלית בתחומים האלה. יש לזה עוד יתרון פה. יש ב-1971 הפעלנו את מצפה וייז במצפה רמון, וחשבתי שהצוות שלנו עוד לא מספיק בשל כדי שרק הוא יפעל ולהביא כמה אנשים עם יותר ניסיון. והיו כמה זוגות שבאו באסטרונומיה עובדים בזוגות לפעמים, והזוג Bahcall גילה, עשה את הזיהוי הראשון האופטי של כוכב משתנה שהיה מסתבר שהוא למעשה פולסר שמסתובב שם בצורך שני. את הידיעה על הגילוי קיבלתי מג'ון במכתב, פתק שהגיע ממצפה רמון, כתוב בעברית טובה, אומר, ה-proper motion בעברית, באותיות עבריות, כזה וכזה, וזה תלוי בחדר, אז מי שרוצה יראה אותו, ויש גם צילום של זה כאן בחוברת הזאת. אז אנחנו למעשה בשנה כמעט 40 גם להישג המטרימוניאלי שלי וגם להישג המדעי של ג'ון, ואנחנו, אני שמח שאנחנו יכולים לחגוג את השנה הזאת באמירה של פרס דן דוד וכל מה שקשור לזה. אז בהצלחה.
Thank you very much, and I call Professor John Bahcall to give his lecture.
If you pardon me, I say just a few words in people to respond to Yuval's remarks, because we've always spoken between ourselves in the group. יובל ואני דיברנו בינינו עברית מאז שהיה לי אוצר מילים פחות מאשר, אני חושב, 100 מילים, אולי פחות מאשר 50. תמיד היה סבלני. אני רוצה כאן הערה קצרה על החזרה כאן לחגוג את הפרס. יובל אמר באווירה, אני לא זוכר, הייתי מילה השתמשת, אבל בשבילנו זו אווירה משפחתית. לראות כאן כל החברים, ואנחנו מרגיש שכל אחד כאן הוא בין המשפחה הרחבה שלנו. אני רוצה גם בשביל הצעירים רק להגיד כמה מילים על יובל בעצמו. אני מקווה שאתם יודעים שהוא אבא של ההרקקים כאן בארץ. זה דבר נדיר לפני עצמו, אבל גם הוא אבא של אסטרופיזיקה כאן בארץ, וזה דבר שאינני מכיר בשום מקום אחר, שבן אדם אחד הוא אבא של חולים שונים חשובים, ובאמת הרמה גבוהה בין-לאומית באותו מקום. זה בזכות עבודתו של יובל, החזון שלו, הוא גם היה אישיות בתוך כל 40 שנה הזו שהשפיע עלינו, כולנו בקהל הרחב הבינלאומי, בהרבה כיוונים, קשרים עם רוסים, וגם הבינו שחלק חשוב של המדינה, היבט חשוב של המדינה בידיים טובות, כי ידענו שיובל וכל הקשורים עליו דואגים גם לצד הביטחוני. I will now see what I'm supposed to do. את לא יכולה לשמוע? אוקיי. Can you hear me now? Okay. Better, but not perfect. כל מה שאמרתי קודם שיובל הוא איש ענק במדע. Okay now? Okay. Okay, I'm going to talk about the development of the answer to the question of how the sun shines. And I will begin in the middle of the 19th century with the debate on the origin of solar energy. Then talk about the original ideas about neutrinos, then how one can use neutrinos to test the idea about the understanding of how stars shine. And then I will talk about searches for missing neutrinos, and finally, achievements and challenges in this area. Our subject begins in the middle of the 19th century with a debate between Darwin, the author of The Origin of the Species, and Lord Kelvin, who was widely regarded by many of his physics contemporaries as the leading theoretical physicist of his day. Darwin argued on the basis of geological evidence and biological evidence that the sun had to be older than 300 million years old. And that was a lower limit in order to make the processes that were occurring in geology have time to take place, and also for evolution to occur. Lord Kelvin had, I think, religious motivations for not wanting to accept this theory, but he also had a very strong scientific argument that this claim by Darwin couldn't be correct. Kelvin calculated the maximum time for the age that the sun could shine, and therefore life could exist on Earth, as being the total energy that you could have by assembling a star of mass m and radius r, which were known for the sun, and dividing by the luminosity. So you take the energy and divide by the rate at which you lose energy, you get a time. And that turned out to be, as an upper limit, 0.03 billion years, a factor of 10 less than the lower limit for Darwin. This was such a powerful argument for Darwin that he was very depressed. He wrote in his letters, personal correspondence to friends and to relatives, that he knew of and understood the reasons for the great reputation that Kelvin had among his contemporaries, and he recognized the power of the logic which said that the maximum amount of energy that you could get from the sun was from gravitation, and that wouldn't last long enough for the evolutionary processes that Darwin thought he had observed. And that was a very depressing thought for Darwin. He had absolutely no answer to it. What he did was, in the subsequent editions of The Origin of the Species, he removed all mention of time scales. He referred to Lord Kelvin on that. We know today that the age of the sun, from measurements on meteorites, is about 4.55 billion years old. So Darwin was correct. Kelvin was incorrect because there were energy sources other than the energy sources that were known at the time for Lord Kelvin. The next key step in the understanding of how the stars shine was made by Einstein and by Aspen. And Einstein, in 1905, in the second paper that he wrote on special relativity, in a very heuristic argument, uncharacteristically heuristic argument in the second paper, he showed that this famous equation E equals mc squared, where you can recognize that a small amount of mass can give you a huge amount of energy. Of course, had no thought that it would be used in the ways that it's currently being used. And in 1920, Aspen, who constructed a mass spectrograph with enormous precision, much greater than had then previously been possible, but to resolve questions about the isotopic distribution, I think maybe among fluorine or some of the moderately heavy atoms that he was interested in. His original paper barely mentions the fact, which was of great historical importance, namely that he found in the course of his measurements, where he made measurements of many different atoms of high precision, that 4 hydrogen atoms are heavier than in helium. And this turns out to be the key step in understanding how stars shine, because from this little extra mass of hydrogen, you can make a lot of energy if you convert hydrogen to helium, which was immediately recognized by many people. So now I'm going to say just a little bit about the original ideas about neutrinos, and then we'll come back to see how that connects with the question of how stars shine. This is a picture of Wolfgang Pauli, who recognized in 1930 that there was a crisis in nuclear physics. There were nuclei with stable state, except for radiation between them, and they seem to have well-defined energy. But when you went from one state to another state, the electrons that were emitted in this transition called beta decay now, those electrons did not have always the same energy. You would expect them to have the same energy if they were everything that came out, because you have an initial state, a final state, and the energy of the electron, and that's the sum of the two final energies ought to add up to the initial energy. That was not the case, and Niels Bohr, for example, suggested on the basis of this crisis that energy was not conserved. And Wolfgang Pauli, in a letter to a Congress which was studying radioactivity, suggested the solution. Incidentally, he did not appear at this Congress because he had his own sense of priorities. He wrote in the early part of the letter that he was unable to attend the formal sessions, was sending his remarks in a personal letter to be read by somebody at the Congress, because his wife had persuaded him to stay in Vienna and attend a dance in Vienna. And so what he proposed was a desperate way out. There could exist in the nucleus electrically neutral particles which would take away part of the energy, and which would then account for the apparent lack of conservation of energy in the decay. These would be very difficult to detect if they were not electrically charged, and that was Paul's desperate solution. This idea was taken up by Enrico Fermi in 1933. Fermi had previously written a very important article called Quantum Electrodynamics that outlined the formalism for that. So he took over the formalism for that to describe the decays in which neutrinos would participate with electrons in ordinary beta decay. This is one of the most important papers in theoretical physics in the 20th century. And all of you who have ever had trouble with a referee, or will ever have trouble with a referee, can take solace from the fact that this paper was rejected by the editors of Nature after advice by learned referees, because it contains speculations too little to be of interest to the reader. And so his paper was first published in a relatively obscure Italian journal, and then later in a longer version in the German journal. And Fermi described in this paper the formalism for weak interactions that we use today with, in a phenomenological sense, only small corrections at the end. Well, there's no significant corrections, very small corrections at the energy that we will be talking about. So how many people here are from areas outside of this? So thank you very much for raising your hand. I'm sure that there are others who... The reason why I wanted you to do that was I wanted to justify the fact that I have this next slide which explains to you what a neutrino is. This talk, it's the talk that I give to Bahcall, not the technical word. Neutrinos are exotic particles. They are produced in ordinary nuclear reactions that we have in laboratories. They're produced in natural radioactivity. They're produced in reactors which generate energy. So they're subatomic nuclear particles. They are very weakly interacting, extremely weakly interacting. And the best way I know to explain to you what that means is to ask you to put your thumb out in front of you. Put your thumb out, extend your thumb out here. And you see your thumbnail, which is roughly about a square centimeter. Every second, 100 billion of these neutrinos pass through your thumbnail, and you never see it, and you never will. So that's one. If you do feel it, there's something wrong. Okay. There are three types of neutrinos, and that will turn out to be important in our story. It wasn't known early on. There are types of neutrinos associated with ordinary electrons, but there are types of neutrinos associated with mu and tau particles, which are heavy electrons, otherwise identical. So there are three types of flavors of neutrinos. Also, neutrinos have enormously small masses. For most of the period in which I've been involved in this study, was believed by everybody who had a strong opinion about it that the mass was identically zero. Now we know that the mass is tiny, is negligible compared to the mass even of the electron, which is very light. But we also know now, as a result of some of the experiments I'll tell you about at the end, that it's not exactly zero. Now we're going to talk about what we will call the neutrino test of how stars shine. So our job now is to connect these particles, neutrinos, with the question raised in the debate between Kelvin and Darwin in the middle of the 19th century. The way we make the connection is through the detailed processes that lead to the production of energy in the sun. The basic theory was outlined by Hans Bethe in 1939. This was after he had written 3 definitive volumes in the Reviews of Modern Physics on all of nuclear physics, and there had been a tremendous development in the theory of quantum mechanics and experimental and theoretical nuclear physics earlier, and Bethe had the insight to select and work out the rates for nearly all of the most important reactions that we now think are determine the conversion of 4 protons to an alpha particle, 2 positive electrons, and 2 neutrinos of electron type, with some energy which is contributed to the star, which is less than 25 MeV, depending on how much energy the neutrinos take away. Incidentally, in Bethe's original paper, neutrinos were thought to be so undetectable that in all of the nuclear equations that he wrote, he never wrote the neutrinos on the other side. Just, I suppose, to save ink at the time. During the 1950s, after the Second World War, Willie Fowler led an international group to measure experimentally the principal nuclear reactions that we think are important in the sun and in other stars. This was an international effort with people at Tel Aviv University and the Weizmann Institute and at the Hebrew University all played important roles. So there was a definition of the nuclear processes that occur in this conversion, and you already see we're connecting with energy, which determines the lifetime of the sun, and now the neutrinos enter this process, so you can see how we're going to make the connection. This is a picture taken in 1965 on mine here of Ray Davis and myself. Incidentally, I have to tell you that now that whenever I give this talk, I always identify the two people there because I gave this talk once in the presence of T.R. Nafi, she's a very well-known mathematical physicist who's been a friend of ours for several decades. And she was sitting in the front row, and I referred to this picture by Ray Davis and myself, and I said, you can see how hard neutrino physicists work by the differences in our opinions, in our appearance between now and then. And then Kiara raised her hand, rather insistently, if you know Kiara. She raised her hand, and in the middle of the lecture, and I called on her, and she asked the most devastating question I've ever been asked in a lecture. She asked me, "John, which one are you?" Now I always say. Anyway, this is a picture of Ray and myself at the bottom of mine, where he constructed a tank which we will see in a minute. And the reason why I put this up here is in 1964, Ray and I proposed that we would use these neutrinos that we were talking about to look into the interior of a star and thus verify directly the hypothesis of nuclear energy generation in stars. We're going to use the fact that neutrinos are so weakly interacting. Remember, we verified that experimentally by extending our sun. To look right down into the interior of a star, which you can't do with light because all the matter is opaque and the light doesn't get out. You look right down into the interior of the star, and you get a direct measure of the rate of the nuclear reactions in those stars by determining how many of the neutrinos come out. The reason why I quote the motivation from our two papers in the Red Letters in 1964 is that we missed the main point. This is what got us started, but what has everybody so interested in the subject in the last decade and a half, 2 decades, has been the connection with particle physics, which we never imagined at the time. I think you will see, I hope you will see throughout this lecture that the way science advances is like a random walk, bouncing around from different directions. And the final place that you get, if you're lucky, will be very far from the place that you intended to get. So this just emphasizes this to you that what we're using neutrinos for is to look right down in the center of the sun, where the temperatures are the highest, the nuclear reactions occur, and to measure the neutrinos that come from here as a measure of the rate of the nuclear reactions. On the outside of the sun are all the features that we can see in ordinary light. But they come from a tiny, thin shell on the very outer regions where the light can escape. Now I'm going to talk a little bit about underground observatories, and I'm going to have to explain to you why we do all of these experiments in an underground observatory. And just for fun, I'm going to ask only the students here who are not in physics, and there were some. Is there somebody here who is not in physics who can tell me why we would have to do these experiments underground? Surely, chemists, okay. My explanation for the lack of volunteers is that you are so overwhelmed by the presence of the senior people that you're not saying what I hope you recognize, namely, since neutrinos are very hard to detect, we put such detectors deep underground where nothing else is happening, in particular where cosmic rays do not reach, so that we don't confuse the very rare neutrino events with cosmic ray or other events that occur on the surface of the Earth. So this is the reason why the experiments that we're going to talk about are all done in underground observatories. This is a picture of Ray's tank underground. This is Ray again down here. And what he does is use 600 tons of perfluorethylene, an ordinary cleaning fluid, which contains components of chlorine-37 to detect neutrinos by the inverse of the beta decay reaction, which occurs normally where argon-37 captures an electron from a bound orbit. Neutrinos will drive this reaction backwards. And when I calculated the cross-section for this plus the expected flux of neutrinos, it turned out that he would expect a few events per day in this tank, which is about the size of an Olympic-sized swimming pool. He had to get a few atoms of argon out of there. At the end of the month, he may have 5 atoms or something like that, because they decay at the same time that they're being built up. So this is what he measured in units of what we predict now with our standard solar model and the theory of standard electroweak interactions. Incidentally, for the major part of this lecture, I'm going to assume not only the correctness of our standard detailed model of how the sun shines, but also the correctness of the standard theory of electroweak interactions, which you read in the textbook. So I assume that both of those are accurate and complete in order to be able to give very specific predictions. We'll find that that's not true for one of the two assumptions, one of the standard models at the end. So this is what predicted for the rate, or this is what is measured. About a third of our standard predicted rate was measured for the chlorine experiment by Ray in an experiment that has lasted about 3 decades. This gave rise to a problem of the search for the problem of the missing neutrinos. Willie Fowler once called it in an article the mystery of the missing neutrinos. And there was a crisis that became more severe because on the one hand there were the models for the sun for which we calculated, we thought, robustly and would precisely define uncertainties in the prediction, and on the other hand there were measurements by Ray which showed that this was not the right rate. And there were 2 general options. One was that our model of the sun was wrong, or two, that our model of our understanding of neutrinos was incomplete. And so there was a hiatus of about 20 years from the time that his first measurements were made in 1968, which showed a factor of 3 difference between our results and his measurements, a factor of 3 which exists today, and the next measurement. And during that time, Ray and I spent most of our time refining our particular numbers. The first experiment that was done to help resolve the problem was led by Professor Toshiba in Japan, and with a collaboration with American physicists. They had a tank of very pure water in an experiment called Kamiokonda, which was designed to detect proton decay. The NDE means nucleon decay experiment. This was an experiment that was designed to observe the decay of the proton. When it was successful in doing that, they converted it in 1986 to be a neutrino, neutrino detector. What you see here, what made the experiment possible, these are very large phototubes with very great sensitivity that were built, especially under Professor Toshiba's direction by Japanese industry to enable the nucleon decay experiment to be very sensitive. What we see here is the bottom of this tank of very pure water before it was filled, and these are the very large photomultipliers. Professor Toshiba had the insight to recognize that not only could the detector detect events of order 100 MeV or so, as they were looking for proton decay, but also with some modifications detect neutrinos of 5 to 10 MeV, which you would expect from solar neutrinos. And they had enormous, to show you what enormous insight he had, he decided ahead of time, which I thought was absolutely incredible, that the detector would begin working on January 1, 1987. In the United States, no one ever says when an experiment is going to start, but they made the major corrections to the experiment so that it in fact started in the middle of December 1987. And why I say they had such enormous insight was 60,000 years before, in the Magellanic Cloud, there had been an explosion of a supernova which gave off neutrinos, 11 of which were captured in his tank in February 1987. This was an enormous achievement made possible by the fact that he got his detector ready then. It's never been seen since. And so it was really important that they got the detector ready on time. This detector measured 0.55 of our predicted rate, and I want to call your attention to the fact that this detector is sensitive to neutrinos of all types, primarily electron type. I just put a subscript here. Primarily electron type, but with about 15% of the efficiency with which it's sensitive to electron type neutrinos, it's sensitive to those other two types of neutrinos, mu and tau neutrinos. So that will turn out to be important for us because you can see that this number is bigger fractionally of our predicted rate than the number of the chlorine experiment. That experiment, by the way, was first reported in the late 1980s, I think it was 89. And shortly thereafter, the first result of an experiment carried out in was originally the Soviet Union, was reported. This used, I should have said, in the Davis experiment, the threshold of energy for the neutrinos was 0.8 MeV, 0.814 MeV. And it measured all energies above that radiochemical experiment. There was no discrimination in it. The threshold for the Kamiokande experiment was 6.5 MeV. After the persistence of this conflict between theory and experiment for more than 20 years, it was decided by everybody in the field that the most important experiment next to do was an experiment sensitive to the very low energy neutrinos, whose flux or number I thought I could calculate to 1%, which was very reliable as photon-photon neutrinos. And the only way understood at that time to do so was with gallium, a detector made primarily of gallium, and that was first done in an experiment in the Russian Caucasus region underneath the highest mountain in eastern Europe. And the Russian, at the time that the experiment was proposed, because we needed a minimum of 30 tons of gallium in order to do the experiment, and the total world production of gallium per year for all purposes was 10 tons per year. The Russian system being very monolithic in the communist age, they decided simply to build a factory dedicated solely to producing gallium for this experiment. And they produced 60 tons of gallium, which are in these detectors in this underground laboratory. Incidentally, the name of their experiment was, it was originally called the Soviet American Gallium Experiment, so SAGE. And when the Soviet Union collapsed, and they considered calling it the Russian American Gallium Experiment, they decided that that would be the wrong acronym. So this is the number that they found. They found for neutrinos of somewhat different energies and different neutrino sources, again, a number of about half of our predicted rate. These are the latest numbers. They are not the original numbers. And a similar experiment done in very similar technique, also a radiochemical experiment, this one experiment. But instead of being done with metallic gallium as the Russian experiment was done, this was done with gallium chloride. I should say that the technique for the Russian experiment was invented by Israel Ostrovsky at the Weizmann Institute. And the Weizmann Institute, under the leadership of Israel Ostrovsky, played a big role in both of these experiments for, I think, political reasons. Israel's name does not appear on the list of authors for the Russian experiment, but in every talk, the historical talk, his important contributions in providing radioactive free material is always acknowledged. And he was one of the leaders of the organic experiment, which was carried out in the Grand Sasso underground laboratory about an hour's drive north of Rome. And for them, the answer also turned out to be a little more than a half of our predicted rate. The solution to this problem began with the Super-Kamiokande experiment in Japan, which is about a 30 times larger experiment than the original water syringe detector in Japan. And the Kande experiment is again an experiment sensitive to neutrino electron scattering. What you see here at the bottom of the detector is water which is beginning to fill this 35,000 ton tank of very pure water, and some of the experimentalists are cleaning the photomultipliers on the top before the the experiment slightly more. This experiment got an answer, again, for higher energy neutrinos initially about 6.5 eV. Now they're down to 5.5 eV, about half of the predicted rate, but with very high precision. And recall again that they have a small sensitivity to neutrinos other than the electron type neutrinos. The Sudbury Neutrino Observatory is a truly unique observatory. It has 1,000 tons of heavy water inside the acrylic vessel that you see here. I show you this particular figure because I happened to be there at the time the figure was being taken. The picture was being taken. Just an awesome sight. You see the scale of the whole detector. This is the lower part of the detector. The whole detector is about the size of a 10-story building. And this is the outer detector where ordinary water fills the region between the inner detector with heavy water and the outer water region. And then the inner region is again flooded down here to prevent radioactivity from the wall. And there are about 10,000 photomultipliers here in the outer region to look for flashes of light produced by the fast-moving electrons in the water that create CERN-caused radiation. And the detector has two modes of operation. The first mode of operation is detecting just electron-type neutrinos. No subscript here. By electron-type neutrino being captured, producing two photons and electrons. And for that, they get about 1/3 of our predicted rate, a number very similar to what Ray got originally back in 1968. But they have another mode which is very special. Both of these modes are very special to the detector. They have energy measurements for their what's called the charge current mode here, where they look just at the electrons and therefore look just at electron-type neutrinos. They have energy resolution here, so this tells them the energy and the number of the neutrinos. They have another mode which is less discriminatory. It measures neutrinos of all types equally by this reaction. It's the equivalent of just disintegrating the heavy water into its components. And so it counts all of the neutrinos of all types that come from the sun. And for that, they measure the number which is in very good agreement with the standard model prediction. It's within 1% with an uncertainty of about 12%. Well, now we're going to get back to our original question. What we have learned from these neutrino experiments is some details about a very rare flux of boron 8 neutrinos produced according to the models in about 1 in every 10,000 of these reactions which burn hydrogen through heating. So it's not important for the energy generation. It's just a rare indication of what is happening in the nuclear reactions in the sun. It is very sensitive to the temperature, central temperature of the sun on the 24th power. And in 2001, the Still Collaboration announced their first direct confirmation of the solar neutrino problem. And just for background, our standard model packet published fortunately, the latest version published fortunately a year before that, was a prediction in the convenient units of 10 to the 6th per square centimeter per second of 5.05 plus or minus about 1. So 20% uncertainty centered on 5.05, and the measurement was 5.44, again with about 20% uncertainty. this used measurements, combined measurements of the charge current through the electron neutrino flux and the superchemiocon measurement. So this was the initial breakthrough, and that persuaded essentially everybody that the solution to the solar neutrino mystery was in fact in particle physics and not in astronomy, and the agreement was embarrassingly good because our era was, the eras in the two theoretical and experimental determinations were much greater than the difference between them. That got worse in 2002, if you can use that expression in this context, because in 2002, this no collaboration published the results of this neutral current measurement, the one which is insensitive to the type of neutrino, measures neutrinos of all types, and as well as their measurement of the purely charge current or electron type. Two measurements, you can work out how many you have in the purely electron type neutrinos and how many you have altogether. And they did that, and their number was even closer to our predicted number, which is purely accidental, we hope. Their errors and our errors are both robust and real, so this is just accidentally good agreement. So, what do we think happens? So we think what happens is that neutrinos that start off as electron-type neutrinos from the sun somehow transform into muon-type neutrinos on the way to the Earth from the sun. Neutrinos and muon and tau neutrinos are much more difficult to detect than electron-type neutrinos. That's why Davis, in his original experiment, which only looked at electron-type neutrinos, had a smaller number than the predicted number based on the theory. Now I want to summarize the achievements and the challenges of the field over the last roughly 40 years. And I'm going to do that by first describing a recent result from a Japanese-American experiment, collaborative experiment, carried out with reactors spanning neutrinos. And this experiment is called Kablin, and it uses the spanning neutrinos produced in reactors spread throughout Japan and the neighboring countries to measure how many of the spanning neutrinos that are produced in this fission reactor actually get to the detector in the form in which they are created. And using those measurements, which show that there is a discrepancy if you don't correct the standard model of electrolytic interaction, to take account of neutrino oscillations, one can refine the inferences about the solar neutrinos, and in that case, the uncertainty in the inferences about the solar neutrino fluxes is less than 6%, and we can put a strong upper limit on a very ugly idea, but one which has been consistent for many years, that neutrinos might come in a different type called sterile neutrinos, which would be even harder to detect than ordinary neutrinos. And in addition, this beautiful Japanese-American experiment showed that the parameters which determine the change of personality or the change of type of neutrinos on the way through the Earth from the interior of the Sun, those parameters are well determined by this experiment, and only one set of parameters called what is now referred to as the large mixing angle set of parameters is now acceptable. So I'm now going to summarize what I think are the main achievements of the subject since first proposal that it was feasible in 1964. First of all, the main achievement is that solar neutrinos are detected. Mind you, that's certainly the only reason that Ray and I considered this subject. And the fact that solar neutrinos are detected with the numbers that are expected based upon a detailed model of how the sun shines via nuclear reaction is the experimental answer to the question raised by Darwin and Kelvin in the middle of the 19th century about how in Antarctica, deep under ice, and at least one in Argentina, all of which will be sensitive to very high energy neutrinos that come from us, not from the sun, but from the very most distant parts of the universe. And incidentally, the leading authority on neutrinos from the most distant parts of the universe at high energy is Ellie Waxman from the Weizmann Institute. So, in a very modest way, we have initiated nearby neutrino astronomy, but we hope that it played a role in encouraging these more distant experiments in the future. We know that the reason why now that the answers differed between the theory and the experiment in the initial stages was that the physics that we were using initially, and probably still is in most of the textbooks, needs to be corrected for the fact that neutrinos can have mass and can change their type, and that many of them that come to us from the interior of the sun are not electron-type neutrinos, but more difficult to detect neutrinos of other types. And the measured flux of this rare branch of neutrinos occurring in about 10 to the minus 4 of the conversions of hydrogen to helium has been measured and found to be predicted accurately by the standard model of the sun. My own work now, in large part, concerns what the next steps to be done in neutrino astronomy, both at the high energies in which Ellie is the expert, and in low energy, where there are a number of international experiments, new experiments to be done in the future. The goal of those experiments are to refine our understanding of neutrinos, which we have to have in order to interpret the neutrinos for their astronomical information about the sun, and to go back to the original proposal that Ray and I made in 1964 to use the neutrinos to teach us things that we can't otherwise learn about the interior of the sun. So I'd like to summarize the talk in a way that was expressed most clearly by T.S. Eliot, and I will read it to you because it summarizes this Mahakam, this circle that we're in this subject, and I think in many subjects. And what Eliot said in the four quartets was, "We shall not cease from exploration, and the end of all of our exploring will be to arrive where we started and know the place for the first time."
Thank you very much. I think we have time for a few questions. Any questions?
You said that you had sort of a few experiments regarding other types of neutrons coming not only from the sun. How does the detector determine where the neutrons are coming from?
Where the neutrinos are coming from?
The direction of it.
Yeah. neutrinos have energy large compared to the rest mass energy of the particles that they hit. So everything goes in the forward direction, all the radiation goes in the forward direction, so you trace back in the other direction.
No.
So you mentioned twice in your talk that the results are embarrassingly accurate. Why is it embarrassing? Is it poopery or what?
Is it what?
They too much pride or the afraid of being wrong?
No. Well, it would have been, let's put it this way. If there had been a measurement of 5.09, and after that we had published a paper which said, we made some corrections to our model, and instead of it being 5.5, it's now 5.05, very close to the measured result. That would be truly embarrassing. So it's just a sense of some awkwardness. I mean, it can happen. Every now and then things can fit better than they should. But our uncertainty is 20%. Their uncertainty is comparable, and yet they fit, to a few percent. Well, that can happen, but not for long.
Any more questions? Yes, David.
Roughly, how many times do you coordinate between those outputs?
Okay, well, that's a very good question. Actually, that picture that I made was made before the latest experiments, which show that the oscillation, the conversion that we think occurs in the sun, mediated by neutrinos in the sun. And the neutrinos really don't oscillate from one state to another state along the way, we think now. Solar neutrinos. I'm sorry. Let me be more accurate than that. At the higher energy at which these experiments are being measured, like about 5 energies, we think that the dominant process in the conversion occurs in the sun in the reactions with electron concentration. And then the neutrinos afterwards are in mass object states where they don't oscillate. At the very low end of the experiments, which we hope to do in heat, it's quite different. The dominant process is the one, at least it's predicted to be, the one that we found illustrated here. And it will be vacuum oscillations, and depending on the energy, they will oscillate a few times between the surface of the sun and the earth. But you need to measure low energy neutrinos to see that particular thing.
In my role as executive environment of the view, Darwin and the direct dynamic connection. Those people, our and my age, remember Wedgwood, the member of parliament from the Labour Party, who stood by Israel through every started nuclear. And so Joshua Wedgwood was Joshua Wedgwood the fourth. The first was the grandmother of Darwin. His mother, Shoshana, was the daughter of Joshua Wedgwood.
Okay, perhaps we should finish and thank the speaker again.